There's something that's radiating, there's something giving out super high speed, probably radiation. Right.
Hey, Professor.
How's it going?
Yes.
Hey, how's it going? Okay, it's 2:30, so let's go ahead and get started. Good afternoon, everyone. How's everyone doing today? Good, good. We're on the eve of the midterm week, and so our midterm is 1 week from today. Okay. So one thing I realized I didn't share with you guys last time was just the general format of the exam. So normally I'm not this detailed. So usually I'll tell you, how many conceptual questions or how many problem-solving questions. But I figure this is probably everyone's kind of first time taking the exam in person in a very long time. It'll be my first time giving exam in person in a very long time. So I thought, let's kind of ease our kind of way back into it. And so what I thought I'd do is just to kind of help you with your preparation. I give you the topics for each of the questions that I plan on asking. So the first thing you'll notice when you open the exam is that there's going to be short answer questions. So very similar to all the homework questions, homework assignments. So the first question that you have there is all short answers. So you can expect them to be in this very same kind of style as that. So that's going to be worth 40% of the points. And then there's going to be 3 problem solving type questions. We're going to have to either compute stuff or derive stuff. And those are the next 3 questions. Okay. And the topics that I've chosen for those questions, the first one's going to be a heat equation type problem. The second one is going to be a thermal circuit type problem. And the last one is going to be a transient heat conduction type problem, which is, the topics that we're going over that we started last Wednesday that we're going to finish up today. Okay. And each of those are going to be worth 20% of the total points of the exam. Okay. So remember, you're allowed to bring a cheat sheet. So you can bring one 8.5 by 11 sheet of notes with you to the exam. You can use both sides. You can write anything that you want on them. You can handwrite it. You can type it. Remember, my only requirement is that you should be able to read it reasonably without, smashing against your face or something like that. Okay? And it will take place in person. You will need your calculator as well. And so I do plan on putting numbers on the exam. And so make sure you bring your calculators to make sure that you can compute those. And besides your calculator, your cheat sheet, and your writing utensil, those are the only things you're going to be allowed to have on the exam. Okay, so just kind of keep that in mind. Okay. And so the plan for today is we're going to finish up our lecture notes on transient conduction. And so this is going to be the general lump capacitance equation, which is what you need to do to solve the very last question on the homework take problem 5. Okay, so any questions on the exam or anything before we get started for today? Yeah. It doesn't matter to me. So you can have a scientific or graphing calculator. It's yeah, you're only gonna use it for basic arithmetic, and so you only need a scientific one. But whatever calculator you feel most comfortable with is okay for me. How long for the exam? And so it's going to take place over the entire lecture period. So you're going to have 75 minutes for the exam. Yep. So we're going to start at 2:30 and then you're going to end at 3:45. Yeah, that's 75 minutes. Okay. Any other questions before we begin? Yeah. Not yet. So I'm still. I was trying to finish up the study guide before the class today, but I didn't get a chance to. And so I'm going to finish it up when I go back to my office, and then I'm going to put up the study guide in the poll at the same time. Yeah. So remember, I do plan on recording a review video this Friday, and so make sure you vote in the poll. Although I put out the poll, but traditionally I put out a poll for a class of 30, 40 people, and only 3 or 4 people answer it usually. And so I feel like I'm just making a review video for 4 people. And so, if you want the review video to be useful to you, make sure you vote in that poll to make sure your voice is heard, right? In our democratic society that we have. Okay, all right. So let's go ahead and get started with the topic for today, which is the general lump capacitance equation. Okay, and so we've been working on this unit on transient heat conduction, right? And so remember, these are situations where we expect the temperature of our object to change with time. Okay. Right, so that's what we were doing last Wednesday. We were only really considering one source of heat, and so we were only basically considering cases where our object is either heated or cooled by convection. Okay. Okay. And so if you remember from last week, kind of the stereotypical case that we were looking at was you take a hot chunk of metal and you dunk it into a cold bath of water, right? And then rapidly that piece of metal, the temperature is going to cool down. Or the opposite, I think we talked about at the end, if you take an ice cube, something cool, and you put it into a warm bath of fluid. And so the fluid is going to heat up that object and the temperature of the object is going to go up with time. Okay. This is fine. So this is good. So this covers a lot of situations that are out there. but it's not the most general case, because you can have a lot of different other time varying situations where you have more than just convection. Okay. Okay. And so besides convection, we can have, like, let's say, for instance, we can have a prescribed heat flux. Right? And so we can have a situation like, remember our heat sandwich from the beginning, from our first homework, right? We have an electric heater that's heating an object, okay, and that's changing with time. Okay. We can have thermal generation, and so we can have an object that is, generating heat on its own, and so that's also going to cause an object's temperature to change with time. And we can also have radiation, right? And so we can have an object that also radiates heat, or maybe it's being heated by radiation as well. And so some instances that come to mind would be like a satellite, something in space that's being heated by the sun. Okay. And so there's a lot. And so in other words, there's a lot more than just convection that we can use to change an object's temperature with time. Okay. And so if I were to draw an image here that kind of encapsulates all of this, and so let's say that we have our object here. Okay. I'm just going to draw a square geometry just for ease of drawing, but this could be almost anything, right? And if we were to draw a control volume around this, okay, and so the green there represents a control volume. What we can do is we can consider all the different sources of heat that can come in. Right? And so let's go down the list, or let's start with what we know. And so we know that we can have convection, right? Remember, convection is any heating or cooling that involves a moving fluid, right? And so convection is going to be modeled by an ambient temperature T infinity and a convection coefficient H, right? So we can have heat loss that goes this way due to convection. And so we've done that so far. Okay. We can have a situation where our object itself is generating heat. And so this would be point number 2 right there for thermal generation. Okay. We can have our object being heated from the outside with the prescribed heat flux. Right? Okay. And so we'll call that Q flux double prime. Okay. Right, and we can also have heat loss or heat gain through radiation as well. Okay. And typically radiation is the way we denote it is, we put like a corner of the room with it. Okay. All right. And so we can have all of these things. And so if we put them all together, or in other words, if we perform our energy balance, and so if we perform our energy balance, we can put all of these together into the same equation, right? Because they're all going to contribute to the heat gain or loss to this to this object. Okay. First, we're going to have the contribution from the prescribed heat flux. Okay, and then what I'm multiplying it here is by some area. Okay. And the reason I'm multiplying by area is I want everything, all the terms in this expression to have units of heat transfer rate. Okay. And so in other words, I want everyone to have units of watts. Okay? remember, heat flux has units of watts per meter square. And so to get rid of the meter square or the units of area on the bottom, I'm going to multiply it by an area. Okay. And the area that I'm multiplying it by in this case is the area at which is being heated. Okay. Because usually when you apply an external heat flux, you're applying it only on a certain part of your object. And so, we're using that area of the part that's actually being heated to multiply with it. Okay. We're going to do an example later where, where this will be a bit more clear. Or what that AQ is. Okay. Next, we have our thermal generation term. And so thermal generation is going to be Q dot multiplied by volume. Okay. Because usually thermal generation is given in units of watts per volume, so watts per meter cube. And so in order to eliminate the meters cube, we're going to multiply it by volume. Next, we have our contribution from the radiation. And so the radiation is already in watts, and so we don't have to multiply by anything. And of course, we have our contribution from the convection. And that's not the same and that's not the same purple, and that's bugging me, but it's too late now. I went paint shopping with my wife over the weekend, and she's like, "Do you like this color or this color?" I'm like, "Babe, they're both blue." Okay, and all this is going to be equal to rho times V times C multiplied by the change in temperature over time. Okay. And that's our unsteady term from our heat equation. Okay. And so what we've done is that we've done an energy balance here where we said, the sum of all these heating sources is going to be equal to the change in internal energy of the object. Okay. And remember, the change in internal energy is represented by a change in temperature over time. Okay. And so far in our lump capacitance framework, we've only considered these two, okay, right? But now we're kind of bringing everyone into the part. Okay, so we're going to consider terms from radiation, generation, and heat fluxes as well. All right, any questions on this so far? Okay, all right. Well, I said that everyone's invited, but we're not equipped yet to handle radiation. Radiation is kind of its own beast, and so we're gonna uninvite him to the party. As sad as that is. And so we're only going to consider these terms right here. Okay. And then in addition to this, we're also going to take our Q convection here and plug in our Newton's law of cooling. Right. Where Newton's law of cooling, remember, is that the heat transfer due to convection is equal to H times the area times the temperature difference. Okay. And so let me go ahead and make those changes. Okay, and so if I make those changes, then we have Q flux multiplied by A sub Q plus Q dot times the volume minus H times A, and we'll call this 8H, okay, times T minus T infinity is equal to rho VC dt dt, okay? Right. Let's perform a substitution just to simplify this a little bit. Although for these problems, it doesn't help us out too much, but it helps us out a little bit. And so we're going to substitute our excess temperature like we have been doing. Okay. Right, so we're going to make that substitution to kind of simplify our convection term a little bit. And so that's going to get rid of the T infinity. Okay. And just so that I get the temperature derivative by itself, I'm going to divide this entire equation by the coefficient there. Okay. And so I'm going to take that rho VC and divide through by the whole thing, just so we get the derivative by itself, because that's a little bit more standard form. And so usually when you're writing out differential equations, whatever your highest term derivative is, you want that to be kind of, I call it like naked, and so you don't have any coefficients. Okay. And so you do all that. And I'm going to do one more thing. So I'm going to take the convection term. And I'm going to move it to the other side of the equation. Okay. Okay, and so we do all that, and we end up with the following. And so we end up with Q dot. Okay. The V's here are going to cancel out, right? And so we have a V that's on top, and since we divided by rho VC, one of those volumes are going to cancel out. And so on the bottom here, we just have rho times C. Okay. Next, we have our prescribed heat flux. And then we're going to have that multiplied by A sub Q divided by rho VC. Okay. So that's everything on that side of the equation. Next, we have our derivative term. And so since we divide it out by its coefficient, then we just have a d theta dt. Okay. And then we have the convection term. So we have H times A sub H divided by rho VC. And then we multiply that by theta, our excess temperature. Okay. And so we do all that, and we arrive at our general lump capacitance equation, okay, or formula, I guess you can call it, which we can use to solve more general cases of unsteady heat transfer. Okay. Okay. So the reason I do this is, just to kind of highlight the fact that before we only had stuff on that side of the equation, but once we add, specified heat flux and also a thermal generation term, then then those get added to the other side of the equation. Okay. Okay. Any questions on how we arrived here? Okay. All right. So I do have a couple of examples. One of them being quite lengthy. But before I jump into that example, I do want to make one important note. Okay, and this is an important one. So you should treat this equation the same way that we treat our heat equation from before. Okay, so what I'm showing you here is kind of the most general form of this equation, but you're not going to include every single term every single time. Okay. Okay. So there's going to be some situations where we have thermal generation, but maybe we don't have any heat flux, or maybe there's some situations where we have heat flux, but no generation. Okay. And so make sure you read your situation carefully. So read the problem carefully to see, what options do you have. Okay. Because it's going to be very rare that you're going to have all of these happening at the same time. Okay. I would say probably the one that's most rare would be the thermal generation term, because that usually requires some kind of special material, which is generating heat on its own, which is not that common in practice, but it can be there. Okay. And you might even have situations where there's no convection. And so if there's no convection, then you're going to eliminate that term as well. Okay. So I think one thing that's useful for when you're using this equation is to look at each of these terms. We have 4 of them here, and then know what they represent. Okay. And so, this term right here, which has our Q dot, this is our thermal generation term. Okay. This term right here is our heat flux term. Okay. The time derivative here, this is our unsteady term. Okay. And this last one here is convection. Okay. Okay. And so if you know what each of those terms represent, then when you come across a situation, you come across a problem, you know when you need to include one term or another. Okay. The only term that's going to be there always, no matter what, is going to be the unsteady term. Okay. So that guy never goes away, unless it's steady state. Okay. But for the other 3 terms, you have to read the question carefully to see, whether this phenomenon is present or not. Right. So whether you have convection, whether you have generation, whether you have heat flux. Okay. Any questions on that before we do an example? Okay, so let's do an example. Okay. All right, so in this example, let's say that it's let's say it's Tuesday night, okay? And you want to save a little bit of money, but you want to impress your girlfriend, right? And so you want to give her a nice meal. And so you're going to cook something up in your kitchen, so you can, maybe make a nice steak or something without having to pay like $50, to really impress someone. A little bit of a side story. So when my wife and I were first dating, I think for our 3rd month anniversary, I took a piece of paper and I wrote on it, you can redeem this for 1 free home cooked meal at a participating Justin's Kitchen. And she saved that. And so it's like, we started dating like over 8 years ago. And she still has it. She pins it up on the fridge and she redeems it almost every single night. Silly me, I didn't put an expiration on that thing or to say that you can only redeem it once, but it's kind of a cute thing for our relationship. Okay. And so to cook a meal, you bring out your trusty cast iron skillet, okay? And you need to heat it up. And so this problem is going to be all about heating up your cast iron skillet. Okay. All right, so the cast iron skillet looks something like this. Okay. You draw a handle on here. So let's say the handle is like this. Okay. So of course you can kind of fill this. Okay. All right, and so to heat up your cast iron skillet, of course, you're going to put it on the stove, and the stove is going to heat your cast iron skillet from the bottom, right? And so let's say here you have a flame, okay? And so what we're going to assume is that the flame is going to impose a heat flux, okay? And so the flame is going to be heating your cast iron skillet from the bottom. And so we'll call this Q flame. Okay. And since it's a heat flux term, we'll give it a double prime there. But at the same time, because you don't want the smoke alarm to go off in your apartment, you're going to turn on the fan, right? And so the fan is going to generate airflow. So if you cook before, there's a hood fan on top. And so that's going to generate an airflow above your cast iron skillet. Okay? And so just as an approximation, let's say that the fan is going to be operating at the temperature of the room. And so that's going to be T infinity. Okay. And the fan has some, some convection coefficient H. Okay. All right. Oh, a couple other things. And so, you know, since the convection, since the airflow is going to be going over the top of your pan, we're going to say this is going to operate on an area called A top, okay? Because that's the surface area at which, you know, the air is cooling your pan. Okay. Whereas the flame, you know, the flame is only heating your cast iron pan from the bottom. So we'll call this A bottom. Okay. Okay. And so at the same time, you know, since you are a scholar / cook, you know what the density of your cast iron skillet is. So we'll call that rho. We'll just call it rho, just to save us some writing. Okay. You also know the volume of your cast iron skillet. And you also know the specific heat. Okay, so all the material properties, geometric properties of your cast iron skillet are known. Okay, and so that's the setup for the problem. Okay, and so what are we solving for? All right, so first, let's you know, since this is a time-dependent problem, let's solve for the time evolution of temperature of the skillet. Okay. And two, let's compute the amount of time it takes to reach a certain temperature. And if you've ever cooked a steak before, you know or really anything over the stovetop, you know the perfect time to put meat or anything into your pan is when the temperature is when the oil starts to shimmer or starts to smoke. And so usually that's the best time to kind of add your food. And so you want to compute the amount of time it takes for the skillet to reach that temperature, the temperature at which oil smokes. Okay. And so we'll call that T oil. Okay. So I'm going to do this entire problem with symbols, but you know, of course, you can plug in all the relevant numbers for all these things. Okay. Any questions on the problem setup? Okay. All right. And so since we have we have an unsteady problem here, so we know that the temperature of the skillet is going to change with time. We know that we're going to use the lump capacitance equation here, right? And since we have heat flux, we know that we need to use the general lump capacitance. All right, so let me go ahead and write out that equation again. And so that equation, we had a Q dot over rho C plus Q flux double prime times AQ divided by rho VC. Okay. This is equal to d theta dt plus H AH divided by rho VC theta. Right? And so that's our general lump capacitance equation, that we showed out kind of before we started this example. Okay. All right. And so when you're doing these kind of general lump capacitance problems, I want you guys to start with this full equation. So, I think it's good practice to write out this full one, and then, cross out some terms. But I think the tendency for people to do is to kind of start from a point that's later on. But, for these problems and heat equation problems as well, I want you guys to start with the general one and then use your assumptions and use your knowledge of the problem to kind of cut some of the terms down. All right. And so out of all these terms here, I would say we only need 3 out of 4 of them. And so we need to eliminate one that's not present in this problem. And so what's the term that we can get rid of in this equation right now? Thermal generation, correct. So right now we have a skillet that is not generating any heat. So the skillet itself is some inert material. It's made of cast iron, right? And so we can go ahead and just eliminate that from our equation here. Okay. And then we're left with just these terms, okay? Okay. And so now that we have these terms, I'm going to go ahead and plug in the terms that we actually have in the problem itself, because the terminology that we use in the problem is slightly a little bit different than this. Okay. But if you had numbers in the problem, this would be a good chance to plug in the numerical value for the convection coefficient, for the volume, specific heat, and stuff like that. Okay. Okay, so let's plug in the problem parameters. And so our heat flux here is being provided by the flame. And so let's go ahead and substitute Q flame. Okay. And then the area at which the flame is acting on, or the area that which the flame is actually using to heat the pan, is the bottom of the pan, right? And so we're going to multiply this by A bottom. And this is all divided by rho VC, which is all known. Okay. The unsteady derivative is still there as before, okay? And next we have the convection terms. And so for convection, we have the convection coefficient H, and so it was just given to us as H. Okay. Next, we have the surface area, which is being affected by convection. And so remember, the only part of the pan that's being affected by convection was just the top of the pan, right? And so we're going to multiply this by A top. Right? And then we divide by rho VC, since all of those are still known, and then we multiply the whole thing by theta. Okay. All right. And so now we have this kind of more specialized lump capacitance equation, which we can apply to this specific example. Okay. All right, and so now we need to actually solve this equation for theta. Which is going to be a little bit difficult because unlike the situations we saw last week, this equation is not separable, and so we need to come up with a different way to solve it. Okay. And so if I were to classify this mathematically, the type of equation this is a first order. Okay. It's a first order ODE because we only have one derivative there. Okay. But since this side of the equation here is non-zero, right, because we have the heat flux, what we have is a non-homogeneous first order non-homogeneous ordinary differential equation. Okay. And so if you remember from 308, or I think you covered this in Math 250A as well. There are a lot of different ways that you can solve these equations, but probably one of the first ones that you learned, which works well for this one, is integrating factor. You guys remember what the integrating factor was, or how that works? Does it ring some bells at least? You guys remember the name? Okay. Yeah. No, you got it. Yeah. And so we're basically going to make a new function here. And so we'll call it mu. I think that's the traditional symbol for it. Okay. And what this mu is we're going to take E. Okay. And then we're going to raise it to the exponent of whatever is in front of our term here. Okay. Because usually for these first order differential equations, you have one term which has your dependent variable, which in this case is theta. And so we're going to take our coefficient in front here. Okay. And we're going to raise E to that power. Okay. So we're going to get integral. In this case, the coefficient in front of theta is H, A top, divided by rho VC. Okay. And we're going to integrate that in terms of T. Okay. And so that integral is pretty easy because everything there is a constant. And so H is a constant, A top is a constant, rho, V, and C are all constants, right? And so we end up with H, A top, divided by rho VC. And then that just gets multiplied by T, okay? Right, so this here is our integrating factor. And so what we're going to do is we're going to take this integrating factor and we're going to multiply this by the entire equation. And so the entire equation meaning this guy up here. Okay? And so if we do that, we end up with Q flame double prime times A bottom divided by rho VC. Okay? I'm just going to leave it in terms of mu of T at first. Okay? Okay. Mu of T. Okay. All right. All right. And so why do we do this, right? And so why would we go through the trouble of making this integrating factor and making us do all this right? And so we chose this integrating factor very specifically, okay? Because if we take the integrating factor, and so this is just a side note, so this is not related to the problem directly. Okay? But I think it's good to learn because I remember when I first learned integrating factor, they didn't tell me why we use it. It just said, if you do this, then magic occurs and you can solve this equation. Okay. And so if you take d mu dt, and so you take the derivative of the integrating factor, okay, and so you take the derivative of this guy, okay, by the chain rule, okay, you get that factor to come out in front. Okay. Right, but since we're taking the derivative of an exponential, then the exponential is still there, right? You take the derivative of e to the t, you get e to the t. But since we have some stuff there in front of the t, that comes out through the chain. Okay. Right. So what's unique about this is that when you take the derivative of d mu dt, you get a term that has mu of t as well. Okay, so we have d mu dt is equal to h a top divided by rho VC times mu of T. Okay. All right. And so the whole point of the integrating factor is really just to focus on just the side of the equation with the time derivative. Okay. Because some magic is going to happen, and I'll show you in a bit. Okay. And so when we multiply mu of T by this entire side of the equation right here, we get d theta dt times mu of T plus h a top time divided by rho VC times mu of T times theta. So I've circled those group of terms in red because we've seen that before, right? And so, in fact, the place where we saw it was just right there, right? And so this entire expression right here, I can replace this with d mu dt. Okay? And so what we have in the end is d theta dt mu of t plus d mu dt times theta. And so this form where you have two terms multiplied by each other, where one term has the derivative and the other term has the derivative of the other term, this looks like a product rule, right? And so if you take the derivative of two functions multiplied by each other, we take the derivative of the first function multiplied by the second one, then we add it to the derivative of the second function multiplied by the first one, right? And so what this allows us to do is it allows us to take this guy right here and do like a reverse product. And so what this allows us to do is that instead of this kind of monstrosity here, we can have d dt of mu of t times theta of t. And this is great to work with, because in order to kind of solve for what's on the inside, we just have to integrate once with respect to t. Okay. And so in case you've never seen it before, or maybe it's just been a long time, this is the reason why we use integrating factors, is to get this guy right here. Okay. Because if you can get that guy, then you can do a reverse product rule and you end up with something that's relatively easy to work with. All right, so that was kind of a side question, but we kind of end up in the place where we want. So let me go ahead and bring the other side. Okay. Q Flame was just over there chilling the whole time, just waiting for his time to come out. But now he can arrive. Okay. And so what we have now is Q Flame times A bottom divided by rho VC times mu of t is equal to the exact derivative of mu of t multiplied by theta of t. All right, any questions on integrating factors and kind of why we do this? Okay. All right. So our goal is theta of t, right? And so in order to get this guy out, our next step here is to integrate. We're going to integrate with respect to t. And so if we integrate with respect to t, then those guys are going to go away. Okay. I'm going to do one other thing. Since all of these quantities here are constant, I'm going to bring them outside the integral. Okay. And so on the left-hand side, we have Q Flame double prime times A bottom divided by rho VC. Okay. Integral of mu of t dt. Okay. And on the other side of the equation, we have mu of t multiplied by theta of t. Okay. And so to isolate theta of t, we're just going to divide both sides by mu of t. All right. And so I'm going to go ahead and kind of flip this around. So theta of t is on the left. Okay. So in the end, what we get is theta of t is equal to rho or Q Flame double prime multiplied by A bottom divided by rho VC. Okay. Multiplied by 1 over mu of t times integral of mu of t dt. And so we've done all this, without even plugging in for mu of t yet. And so that's going to be the last part. And so since we know what mu of t is, we can go ahead and plug in for it. Okay. We're going to plug in for mu of t and then carry out this integral here on the left. And so just to kind of remind you, mu of t, so you don't have to kind of scroll up. Mu of t here is e raised to the h a top divided by rho vc t. Just because, you know, it's a little bit, it's kind of a lot to squeeze into the exponent there. I'm going to use a notation, which you might have seen before. And so whenever you have e raised to a certain number, you can represent that by putting exp, and then inside the parentheses, you put the exponent. Okay. And so exp and then brackets h a top rho vct is the same thing as e raised to that same quantity. All right, so let's go ahead and plug it in. And so we have theta of t is equal to q flame times a bottom divided by rho vc. Okay, we have 1 divided by e, and so we have exponential. Okay, since we have 1 over this, I'm just gonna put the negative in the exponent, and so this is 1/8 exponential of negative h a top divided by rho vc t, okay, times integral of exponential h a top divided by rho vct dt. Okay. Okay. All right, let me pause here for a second. Are there any questions on kind of where we're at on this example? Okay. Okay. And so the next step is we're going to carry out this integral. And so we're going to do the opposite of the derivative here. Okay. And so to carry out that integral, we're going to take the coefficient in front and we're going to multiply by 1 over that. And so we get a rho vc divided by h a top. Okay. And that's going to be an exponential of h a top divided by rho vc t. Okay. Let me make that a little bit clearer. And since we're doing an indefinite integral here, or in other words, you know, we're not integrating with respect to any bounds, we're going to add a c to that. Okay. Okay. Okay, so let's go ahead and multiply this by the rest of our expression here. Okay. And so we have a rho vc up top here. We have a rho vc on the bottom there. Okay, so those are going to cancel out. Okay. Since this is just a constant, I'm going to take the denominator here and just add it to this coefficient in front here. Okay. And so we have theta of t is equal to q flame double prime a bottom divided by h times a top. Okay. We put a bracket here. All right. So first term in this expression, we have an e raised to the h top over rho vct. We're going to multiply that by e to the minus h a top or rho vc t. Okay. And so this is just going to be a 1. Okay. And then on the other term, we have a plus c times exponential h or minus h a top divided by rho vc t. All right, and I'll pause here for a second because this right here is our general solution. It's a general solution because we have it in terms of an arbitrary constant C. Okay? And now we're going to need to apply an initial condition to solve for that constant C. Okay? All right. So this problem ended up being more work than its innocent beginnings. Okay. Any questions on any of the math that we used to get here? Yeah.
Thinking the negatives inside of the exponential on the side, right?
Yes, it's on the inside. Mhm. Yeah, that's going to be important because we need to have a decaying exponential. Yeah.
I'm a little confused where the negative came from.
Yeah, so the negative came from the fact that we have 1 divided by mu of t here. And so when we take, our I'm just going to do, our integrating factor was something like this, right? So we had e raised to the something times t. And so we take 1 over that. Another way to express this is e to that negative. Yeah. Okay. All right, so let's go ahead and solve for C. Okay. All right, so I didn't mention any initial conditions, but one reasonable initial condition, if you can kind of think of, if you're kind of, taking out a pan out of your cupboard to cook with, right? A reasonable assumption is to say that your pan at the beginning, before you turn on the flame, is your pan is going to have the same temperature as your pan. Okay? And so T of 0 of the pan is going to be T infinity, right? And so if the pan is going to start at T infinity, what this tells us is that theta of 0 is going to be equal to 0. Okay. All right, so let's go ahead and plug that in. So we have theta of 0. Okay. It's going to be equal to Q flame, double prime, A bottom, divided by HA top, multiplied by 1 plus C times E raised to the 0 power, right? Because we're plugging in 0 for T. Okay. And we know that E to the 0 is just 1. Okay. So we're just going to cancel that out. And all this is going to be equal to 0. Okay. All right. And so the first thing we can do is we can take this guy and we can divide both sides by that because it's a coefficient in front of all those terms. Okay. And since the other side is 0, we're going to just kind of cancel that out. Okay. And so in the end, we have 1 plus C is equal to 0. And from this, we can see that C is equal to -1. Very simple. Okay. All right. And so let's take that C and let's put it all together. And so we put it all together, we get theta of T is equal to Q flame, double prime times A bottom, divided by H times A top times 1 minus exponential of minus H A top divided by rho VC T. Okay. And that right there is our final solution. Question, so why did I cancel the Q flame? Are you talking about for the boundary condition term up here? So the reason I crossed it out is because on the other side of the equation, we have 0. And so what I did for this entire term right here is I divided both sides by this. Okay. Yeah, so if you divide both sides by it, it cancels out because it's 0 on the other side. All right, so let me plot this, because I think you kind of get a full appreciation for what it looks like once you. All right, and so on the x-axis I have time t, and then on the y-axis, excuse me, we have temperature. Okay. We're going to start at 0 because we assume that our pan is starting at room temperature. Okay. And if you plot this, I'm basically plotting this term right here. Okay. What you get is something that looks like the following. So you have kind of a rapid increase, and then it starts to taper off, and then you reach basically a steady state. With this line right here, the value of this line the value of that line is Q flame times A bottom divided by H A top. Okay. And so how do I know that that's what the value of the steady state is? Let's look at this term right here in brackets, right? And so we have 1 minus a term that is a decaying exponential. Okay. And so what happens when we plug in a large value of t? Right? And so we have e raised to the minus times some very large number, right? And so since it's a decaying exponential, we know that for large times t, this term here is going to go away, right? And so for large times, all that we're left with is 1 multiplied by the coefficient of, which is how I got that steady state value. Okay. And so when you have a situation like this where it reaches kind of a what I call like a steady state, or it reaches kind of a steady value over long times, okay, this is what's known as the steady state or steady state solution. Okay. Because after kind of the initial heating up period, then the pan kind of persists at this temperature. Okay, it doesn't go above or below. Okay. All right, and so what does that mean? And so when the skillet reaches steady state, that basically means that all the thermal processes, that are occurring on this pan have reached equilibrium. And so for this particular problem, we had 2 kind of competing forces, right? And so we had the heating from the flame on the bottom, right? And so that's heating up the skillet, but at the same time, the skillet is being cooled by the air that's on top. Okay. And so when the skillet reaches steady state, all that means is that the heat gain from the flame is perfectly balanced by the heat loss due to convection. Okay. So the amount of heat coming in is exactly equal to the amount of heat coming out. Okay. And so when it does that, it persists at this kind of steady state, at the steady state temperature. And so that's something to look out for all these transient problems. And so, based on the limitations that we have in this class, we can only solve problems that kind of look like this. And so eventually the problem will reach a steady state solution. Okay. So for the problems that we looked at last Wednesday, the steady state was when whatever object they were looking at had reached the same temperature as the fluid, right? We looked at our chunk of metal and we looked at our, our ice cube, right? And so that reached steady state just whenever it reached the same temperature of the fluid. Here, since we're introducing some heating elements, the steady state is just whenever those heating elements are perfectly balanced by the convection cooling or convection heating, whatever we have. Okay, any questions on this? Okay. All right, so I know there's one more part to this problem, and so the other part of the problem was to find out, the time at which this temperature will reach a certain temperature, and so we can solve for that basically the same way that we've done before, where we set theta out here. Does it do this? Okay. And so to solve for a time when temperature reaches a certain point, okay. All you have to do is plug the desired temperature in for theta of t. Okay. Then you're going to take that equation and solve for the t. Okay. So I think we did an example for that like that last week, because I do want to show you an example really quickly of a case where you don't have convection and what that looks like. Okay. And so I want to make sure we get to that example, but I don't want to leave you hanging. So that's how you would basically solve for that t. Okay. And so, the details for that, if you look in the lecture notes, the details for that are in there. But I did want to show you a case without convection, because problem 5 in the homework does include a case without convection. So, I want to make sure you guys know how to solve those problems. Okay, so any final questions on the skillet before we move on? Okay, all right, and so that's it for the skillet. And so let's do another example. This one won't be nearly as long, I promise. Okay, and so this is going to be example without convection. So this is just to kind of show you a case of, if you don't have convection, what does the solution look like? Okay. And for this example, I'm going to use a popular commercial item. So if you've ever gone hiking in the mountains or where it's really cold, you might have used a device called the hand warmer. And so I think it's marketed towards hikers, but honestly, it's kind of nice if you're kind of cold in your apartment to kind of warm your hands. Okay. And so the way it works is that it's sized about the size of your palm. Okay. And you wear it underneath a glove. So the assumption is that you're wearing some kind of glove on your hand, and then the hand warmer kind of slips in between your palm and the glove. Okay. And so it looks something like this. And so let's say that you have your hand. 1, 2, 3, 4. Okay. Okay. And so you're going to add the hand warmer. That's a hand. Come on now. Come on now. And then you have a glove on top of it. Okay. So I'm going to draw a exaggerated glove because the glove should be bigger than your hand. Okay. And so you put the hand warmer on your hand, you put the glove on top of it, and then you have warm hands. And so that's really nice. Okay, and so what we want to do is we're going to assume that the hand warmer is generating heat. Okay. So there are some electric ones. So there's ones that run on batteries. And so those ones are basically transforming the electrical power into thermal power. I know that there's some that are chemical as well. So like very similar to like a cooling pack if you've ever used one. But this is just the opposite in that it's heat. Okay. And because this hand warmer is being shielded by the glove, we're going to assume that there's no convection here. Okay. And so what we're interested in we're interested in computing the time evolution of temperature for the hand warmer itself, so for the device. Okay. All right. Any questions on the problem setup besides the obvious critique of my artistic skills? Okay, hands are hard. So my wife's an artist, and even she says drawing hands is hard. So I don't feel bad about this at all. Okay. All right. And so just like we did with the pan, we're going to start with our general lump capacitance equation. And so we have d theta dt plus h a h divided by rho vc times theta is equal to q dot over rho vc, or excuse me, over just rho c plus q flux double prime times AQ divided by rho V. Okay. All right. And so the problem has already told us that there's no convection, and so we can go ahead and get rid of this guy. Right. We do know that there's thermal generation, right? Because we know that the hand warmer is generating heat on its own. Okay, so we know we're going to keep that guy. What about this term? So what about the heat flux term? And so are we going to, are we going to have a heat flux term here? What do you think? I see some lot of unsureness. And so, what the purpose of the hand warmer there is to warm your hand, right? And so a lot of the heat that gets generated by the hand warmer is going to go into your skin, right? And so all the heat that gets generated by the hand warmer is going to be absorbed by your skin. And so we can say that this here is a heat sink, right? Because it's going to be taking away heat from the hand warmer, right? And so to represent a heat sink, I can just change the sign on this. So we'll call this Q skin double dot times AQ divided by rho VC. Okay. And then we have an equation that looks like that. All right. Because your skin is going to be absorbing the heat from the hand warmer, and so the hand warmer is going to be generating heat, and then the heat that gets generated, because none of it's going to come out to convection because it's covered by the glove on one side, but it's going to be going into your hands, on the other side. And so what we're doing is we're only doing our thermal analysis on just the hand warmer itself. And so since the hand warmer is in direct contact with your skin, the skin is going to take away some of the heat from the hand warmer. And so that's what that represents. And so I guess if you want to be specific, then this AQ right here would be like the area of your palm. Because that's the area that's in contact with the hand. Okay, any other questions on how we got this equation here? And of course, this is assuming that you know the thermal generation rate and you know the density and the volume. And so we're going to assume all of this is known. Okay. Okay, and so now that we have this, we can go ahead and solve for theta. But luckily for us, we don't have any convection. Okay. And it turns out convection is the thing that's most difficult to solve with these things. Okay. And so what we can do, since all of this over here is constant, we can just simply separate the variables. And so I'm going to take dt and I'll move it to that side of the equation. And so on one side we have d theta is equal to d theta is equal to q dot over rho c minus q skin double prime divided by or multiplied by a palm divided by rho vc times dt. Okay. And so what we can do is we can integrate this. And so on the left-hand side, we have theta of t. On the right-hand side, since all this is a constant, when we integrate this, okay, we end up just multiplying the whole thing by t, okay? Right, and just very quickly, just since we're running a bit short on time, if we assume that theta of 0 is 0, that's going to get rid of the c term right here, okay? Right, because remember we add the c term just because it's an indefinite integral, right? And so if we do that, then we're left with the final equation. Okay? The final equation or the final solution would be something like this. And so you just have a linear ramping a linear ramp here that ramps up with t. All right, question. So what would change if we looked at the entire hand instead of the warmer? Yeah, that would be challenging because then you have an inhomogeneous solid there. And so some parts of your domain will be generating heat, whereas the other parts of the domain are not generating heat. And so you can do situations like that. It's just you would kind of have to solve it kind of separately. So you would kind of have to solve one situation for the hand and one situation for the warmer, and just kind of couple their solutions, just through kind of an exchange of heat. And so, it's possible, but it's a little bit difficult. Okay, any final questions on any of this? Okay, and so that should give you everything you need to do the last problem on the homework. Because remember, the homework is due on Friday. Okay. Yeah, and so the only thing with these problems is, make sure you're reading them carefully and make sure you only include the terms that are there, okay? And if there's numbers in the problem, you can plug them in as well. All right, so thank you everyone for tuning in today. That wraps it up for first midterm content. And so as of right now, nothing that we cover on Wednesday is going to be on the midterm. So Wednesday we're going to start something new, but that's not going to be on the midterm. So today's the cutoff. So after today, nothing on the first one. All right, so thank you guys for coming. Hope you guys enjoy the rest of your day, and I'll see you on Wednesday. you're a better artist than I.
No, it's a song.
Oh, it's a song. Oh, I see. A sock works too. Yeah, as long as you get your fingers in there. Oh, I see. Yeah, it's yeah.
In all seriousness, so like, do you mean like the heat goes into your arm or something?
Yeah, so like like if you touch anything that's warm, right? So even on like in the extreme case, think of like you're touching a hot piece of metal, right? And so a lot of the heat, because the metal is a warmer temperature than your hand, heat's going to go from the metal through your hand. So this is kind of like a smaller piece of that. The hand warmer is going to be generating heat, and that's going to go through because your hand is at a lower temperature.
And then you said that we're solving in terms of
We're solving for theta, and so but the Q here, this Q flux, that's the Q that goes from the hand warmer into your.
And then also, do you know how to make this on one side? All the way on this side?
Oh, that I have no.
I think
Yeah, no problem. Yes. Hopefully they're staples. Yeah, they're staples.
Thanks.
Yep. Mhm.